Have you ever looked up at a towering tree in a park or maybe a massive building and wondered, how on earth does anyone measure that without a giant tape measure or, I don't know, a helicopter? Well, welcome to the Explainer. Today, we're going to figure out exactly how that's done. We're diving into Grade 9 Geometry, Unit 3, Lesson 3, Special Segments, Proportions, and Indirect Measurement.
Here's our quick roadmap for today. We'll start with our objective, the geometry of measurement, then jump into an explanation of special segments. After that, we'll tackle the tree shadow problem as an example, clear up a common misconception about medians versus altitudes, do a quick formative check to find the length, and wrap it all up with a recap on segments, proportions, and measurement. Let's get right into it.
Section 1. Objective. The geometry of measurement. Our main goal for this explainer is to connect special triangle segments and proportional relationships so you can completely master indirect measurement. Look, we aren't just memorizing abstract shapes on a page today. We're actually building a powerful mathematical toolkit that has real practical utility in the real world. By the end of this, you're going to be able to unlock distances you literally can't measure directly.
Moving right along to Section 2. Explanation. Special segments.
Okay, so the very first special segment we need to look at is the median. A median of a triangle is just a segment that goes straight from a vertex to the exact midpoint of the opposite side. Now, when you draw all three medians in a single triangle, they always meet at one very specific point of concurrency. We call this point the centroid. And you know what's truly fascinating about the centroid? It's the exact center of gravity for that triangle. So, if you were to cut that triangle out of a piece of cardboard, it would balance perfectly on the tip of your pencil right at that centroid.
And this perfectly illustrates the concurrency of medians theorem. If you look closely at the intersecting segments here, the theorem proves that the centroid sits exactly 2/3 of the distance from each vertex to the midpoint of the opposite side. So, for example, the distance from vertex D to the centroid C is exactly 2/3 of the total length of the entire median dj. This predictable, proportional ratio, it's an absolutely incredible tool for us.
Now we really need to contrast the median with another crucial segment, which is the altitude. An altitude is a segment dropped from a vertex so that it is perfectly perpendicular to the line containing the opposite side. It's all about that perfect 90-degree angle. When the three altitudes of a triangle intersect, their point of concurrency is called the orthocenter. And unlike the centroid, which is always safely tucked inside the shape, an orthocenter can actually be inside, outside, or literally right on the edge of the triangle. Crazy, right?
So the big takeaway here is that by understanding the rigid, proportional properties of these geometric segments, we can do some seriously amazing things. And this brings us right to indirect measurement. Basically, this is the process of using proportions, specifically those related to similar triangles, to determine a measurement when direct measurement is just totally impossible or super inconvenient. Let's see this in action in Section 3. Example: the tree shadow problem. Okay. Let's apply these geometric proportions to the exact scenario I mentioned at the start of our explainer. Imagine you want to measure a giant tree at the community park. The source material sets this scene up perfectly. The tree casts a shadow that's 5.4 meters long. You step into the shadow so that the tip of your shadow exactly meets the tip of the tree's shadow right on the ground. You're standing 2 meters away from that tip. Now, if you're 1.25 meters tall, how tall is the tree? Because the sun's rays hit both you and the tree at the exact same angle, you've just created two proportional, similar triangles. It's like a giant puzzle waiting to be solved. Let's walk through the algebra to solve this together. Step 1 is setting up our ratio. We just compare corresponding parts, right? So height over shadow equals height over shadow. Your height is 1.25 meters and your shadow is 2 meters. We set that equal to the tree's unknown height over its 5.4 meter shadow. Step 2, we cross multiply. So 1.25 times 5.4 gives us 6.75. Finally, step 3, we simply divide that 6.75 by 2 to isolate the tree's height. And the result? The tree is exactly 3.375 meters tall. No ladders, no climbing gear required, just a pure power of geometric proportions. Which brings us to Section 4. Misconception: medians versus altitudes. It is so incredibly easy to mix these two segments up, and our source text actually highlights this specific error. You've really got to remember the distinction here. Medians connect a vertex to the exact midpoint of the opposite side, splitting the base perfectly in half. Altitudes, on the other hand, connect a vertex perpendicularly to the opposite side, creating a right angle. Listen, just because a line is drawn straight down from a vertex does not automatically make it an altitude, unless it forms that 90-degree angle.
so always be on the lookout for the right angle symbol or those midpoint tick marks.
Let's test your knowledge in Section 5. Formative check. Find the length.
All right, think back to the theorem we discussed a few minutes ago about medians and centroids. If point A is the centroid of our triangle, and the segment from the vertex to the centroid ZA has a length of 9, what is the total length of the full median segment ZC? Take a second. I really want you to challenge yourself to recall that specific distance rule we talked about. Did you get 13.5? Because if you did, absolutely fantastic work. Let's just quickly break down the math for clarity. The concurrency of medians theorem tells us that the distance from the vertex to the centroid is exactly 2/3 the length of the whole median. So 9 is 2/3 of our total length ZC. To solve this, we can multiply 9 by 3, which is 27, and then divide that by 2, which gives us exactly 13.5 for the full length of the median segment.
And finally, Section 6. Recap. Segments, proportions, and measurement. Let's do a rapid-fire summary to lock this all in. First, medians split opposite sides in half. They meet at the centroid, and they follow a strict 2/3 distance ratio. Second, altitudes drop down at perfect 90-degree perpendicular angles and meet at the orthocenter. And finally, the big payoff. By leveraging these proportional relationships, we unlock indirect measurement. Geometry isn't just about shapes on a page. It is the ultimate tool for measuring the seemingly unmeasurable world around us. So, the next time you're walking outside on a sunny afternoon, look at the shadows on the ground and ask yourself, what giant object could I measure right now? Just by knowing my own height. Could you measure a skyscraper? A mountain? The tools are already right there in your head. Keep observing, keep calculating, and I'll see you in the next explainer.